Hello, Year 10. This is a video to take you through the Year 10 sort of assessment. So essentially this is the mark scheme, and I'm just going to work through the assessment in the way that I think about it, and so you can sort of get a sense of how each question is answered. So let's sort of zoom in and see the things that we're interested in. On the inside cover of your final exam, you will get a sheet of formulae. We do tend to remove the ones that are irrelevant at the moment, and essentially it looks like you've got two. Really, you have one. And the fact that they're both here is really just trying to get you being aware that transfer of energy is the same as work done. They are a sort of an identical kind of thing, which is something that's going to actually come up. The other thing that you've got, if you ever need G, it's 10 meters per second squared, or 10 meters per kilogram, but the number's 10. You've been using that since year 9, so let's have a look at the questions. So first one, we've got a lovely flying squirrel. He's very happy, and we see, yay! Very, very happy flying squirrel. The mass, we've got a mass, it's got a height. What's the equation linking GPE, mass, G, and height? And so that's a recall mark. So it's the GPE equals mass times gravitational field strength times the height. You can do this in words, you can do it in symbols. What you are not allowed to do is do some kind of like, do this. Do not write a formula triangle. That is not an equation. It's not an equation because there's no equal sign in it. So if you're someone who likes formula triangles, be aware that you can't write them down as an answer. They won't get you the mark. Calculate the GPE gained by the squirrel during the climb. We've got our equation, so we'll get a mark for substituting the numbers in. So we get a mass of 0.19 times 10 times 17, which comes out as being 32.3 joules. You can move the answer down there if you really want. As long as it's very clear what your answer is, you're actually fine. Then state the amount of work done against the force of gravity by the squirrel during this climb. Interesting thing to note, this is a 1-mark question, and its key instruction here is state, meaning you don't need to do any really hard. And if we remember what I just told you, that work done is energy transferred, well, we've just calculated the energy that we've gained, so we've just transferred 32.3 joules, so the work done must be exactly the same. It is just 32.3 joules. If you got this number wrong, then this number is fine as long as it's exactly the same number you wrote there. So you can get an error carried forward. So if, for example, you'd forgotten to multiply by 10, so you just had 3.23. If you wrote the same number here, you get the mark for that. Right, flying squirrel glides from P to Q, the constant velocity, not to scale. I mean, otherwise this would be either very tiny trees or a very large squirrel. Actually, that's 17 meters. This is an enormous squirrel. The squirrel, if this had been to scale, the squirrel is about 1 meter high. Avoid the squirrel. Actually, no, more than that. There's definitely more. You wouldn't fit 17 there. Ugh, maybe like 2 meters high. Giant squirrel, bigger than me. Right, state the equation. I'll get on with this now. The equation we're looking for here is kinetic energy is equal to a half times mass times velocity squared. You can write speed, velocity and speed. As far as you're aware of at the moment, they can be the same thing. In year 11, you do y, velocity and speed. They're slightly different, but that's fine. Again, fine to do it with symbols, which is Ke equals a half times m times v squared. You can write 0.5. That's also fine. Calculate the kinetic energy of the squirrel. Again, you're going to get a mark for substitution and then a mark for the calculation. So you've got Ke equals, I'm going to go 0.5 this time. 0.5 times 0.19 times 13 squared, which comes out as being about 16.1 joules. You only need to write 16 because it's to the same number of figures as everything else. But there we go, 7 marks, nice and easy. Hopefully about recall and plugging numbers into the equation. Okay, then we've got something from year 9. We've got a volume of a piece of brass. We've got measures its mass. Mass is 138 grams. Density, mass, volume. So density is equal to mass over volume. Now, symbol-wise, these are a bit different. Okay, density is not a D. It is a sort of a curly P. If you just write a P, it'll be fine. It's called a rho, equals M over V. So it's pronounced rho. It's a Greek letter. But essentially, if you write a P, it looks like it enough, close enough, so no one's going to say anything different. But it's definitely not a D. Calculate the density of brass. Give the unit. So to do that, we'll get a substitution into this equation. So we'll get density is equal to 138 over 16.3, which gives us 8.47. The unit that we want in this case, with our mass in grams, volume in centimeters cubed, grams per centimeter cubed. You've got to be careful. I mean, it's perfectly fine to leave things like this. You could go into kilograms, which is 0.138. Converting into centimeters cubed to meters cubed is a little bit tough. You've got to divide this number by 100 3 times to counteract the fact that it's cubed. But I would leave this one in grams per centimeter cubed. That's fine to leave this in. Okay, so whenever it says give the unit, you are allowed to choose a unit that's easiest to deal with. In this case, it's grams per centimeter cubed. The student notices the electronic balance has a 0 error, so it shows mass readings that are all slightly too small. That means that the density value is which of these? Well, it's going to be B, incorrect and slightly too small. So if it's not really 138, let's say it's really 140, well, then this number would be bigger. So if the true value is bigger than 138, we would have a bigger value for our density. So there we go. And that's number 2. Right, question 3. This is dating back again, a bit of year 9 revision. The LR5 is a specialist submarine for underwater rescues. We've got a density of seawater, kilograms per meter cubed. State the equation using pressure difference, depth, density, and G. So this is so the pressure difference is equal to depth times density times G. As symbols, this is often written as a delta P, so that means change in rho G H is kind of how that's written, but that's fine. You know, it's quite a nice way of doing this. They've literally just written the thing out. You just need to go equal that times that times that, and you end up with the equation. Calculate the increase in pressure over the LR5 descends from surface to a depth of 700 meters. So again, first mark is substitution into the correct equation. So that's going to be depth is 700 times density 1028 times G, which is 10. So you end up with 7196000, I believe, pascals or newtons per square meter. So that's what you get there. So we've got atmospheric pressure is 1 times 10 to the 5. Standard form. Someone's left a message in one of the papers I've written. They don't like standard form. Okay, so this means there are 5 zeros. So this is essentially 100,000. 5 zeros, 10 to the 5. So what do we need to do? Well, we need to add 100,000 to this here. So atmospheric pressure is this. What's the total pressure? This is in existence. This is in the air. Okay, so essentially this is what's happening in the air, and then we've got sort of the water. 700 meters. So we've gone 700. So this is 7196000. So this is just due to the water. This is what's due to the air. The air is still there, hasn't vanished because you've dived underwater. So you add the two, and so you end up with 72960. So it's just adding that one there. It's simply, I can't see it there. This is a 1 mark question. It's just literally for working that out. The LR5 is tested in fresh water. The density of this is there. Explain why the pressure in submarine in the fresh water is less than the pressure in the sea at the same depth. Basically, 1 more question. The density is lower. Okay, so you're going to end up with a smaller number. You're not multiplying by 1,000. You're multiplying by 1028 for seawater. So so there we go. It's nothing. A student is given a sample of liquid labelled seawater. Describe the experiment the student can carry out to find the density of the sample. 5 marks. We're looking for sort of like 5 kind of things to say. This was a standard thing you did in year 9, measuring the densities of things. So first off is first thing you need to talk about is what equipment do you need? Well, you need measuring scales or a balance. That's one thing you need, and you will need a measuring cylinder. Okay, so you need to mention this. You need to talk about a thing in terms of something to how to measure the mass, which in this case is so weigh cylinder, add water, weigh again, and then you subtract the difference. Okay, so yeah, or use 0 to anything that would be fine. I mean, if you've got your balance kind of here, and then you've got your measuring cylinder. Okay, you add the water, and you see, and you read the scale. So either you can sit it on there and 0 and add the water, or you can do it the other way. It's fine. Right. Okay. So that's the second mark. Third mark. Some method in which case you're being accurately using the measuring cylinder. The key there is so measure volume at eye level. Okay, that's because if you look at measuring cylinder, that's a terrible line, and we've got marking there, and you've got sort of markings along the side. If you look below, then you're going to see one value. If you look above, you're going to see another value. It's called a parallax error. So you always need to measure. There's my eye. Excellent. That's what I learned. It's terrifying. You always need to look at eye level. Is the thing I would always say to do. Right. So what have you got? You've got some equipment. You've taken a measurement of mass. You've taken a measurement of volume. So the fourth thing you need to do is, use density equals mass over volume. There's a mark for doing that. And then the final thing that I would say to do is, repeat and average. Okay. Things about this in any of these things, there will always, almost invariably, there will be some marks for saying repeats and average. This isn't the sort of like this isn't sort of like the most generous one. They do have a 6th mark in the mark scheme, which is for talking about the units that you would measure. So in this case, you'd measure it in grams per centimetre cubed or grams per milliliter in terms of what the units would be for density. That's the things that they are allowing. It's a bit meaner because sometimes they would give you marks for saying I'm going to measure the mass, and then a mark for saying how you're going to measure the mass. You've got to talk about both bits of equipment that you need, but essentially, whenever it's a practical, it's always what are you measuring, what are you using to measure it, and then what are you doing with the things you've collected. And that's invariably always going to take you to quite a few marks on any one of these questions. And there we go. That's how we do that one. Right, okay. Question 4. We're on to question 4. So we've got a multiple choice one. Student university forecast. How is energy transferred usefully from the engine of a car to its wheels? Well, it's forces, so it's D, because you're going to push things. The engine of a car burns petrol, which transfers energy usefully from the chemical store to the petrol to the canister of the car. The useful power output of the car's engine is 47 kilowatts. Calculate the useful energy output of the car during a 15-minute period. So, right, so we've basically got two things we worry about. One is this is measured in kilowatts, and this is measured in minutes. So the first mark is from doing a conversion of either of these things. 47 kilowatts is equal to 47,000 watts. Okay, there's a mark for doing that. Or 15 times 60 is equal to 900 seconds. So there's going to be one of those. We have to do the conversions because this is in joules. It's not in kilojoules, so we have to do these conversions. So that's one mark. The second mark is for substituting it into the equation that you're given. Okay, so we're given the equation that power is equal to energy over time. So that gives us energy equals power times time. So you can substitute it in. I should actually do that first, really. The easiest way to always get the marks is to substitute in first. So I should really do 47,000 is equal to energy over 900. So that gives us, by a rearrangement, energy is equal to 47,000 times 900, which comes out as being 42 million. Okay, so the first mark is for a conversion of either, the second mark is for that, the third mark is therefore for getting the correct answer. If you fail to convert one of them, then you'll still get 2 marks out of 3. Okay, so state the formula linking efficiency, useful energy output. So efficiency is equal to useful out over total total output or total input, which is a it does allow you, it's a bit fiddly there, but it says output here, and you would have been taught it as energy input. Total is always the same, total out or total in. The mark scheme allows both because that's a very strange way of phrasing it. And then you can then write times 100. Okay, it's correct even if the times 100 is not there. During the 15-minute period, 2.0 times 10 to the 8 joules of energy is transferred from the chemical store of the petrol. Calculate the efficiency of the car's engine. So the total input is 2 with 8 zeros. Okay, so the efficiency is going to be 42, 1, 2, 3, 4, 5, 6, which is the number we got up here, divided by, and then we've got 2 times 10 to the 8 is 2, 1, 2, 3, 4, 5, 6, 7, 8. I've done my commas the wrong way. Just so you're aware, there is the ability to get an error carried forward. If you've got this number wrong, but you put it there correctly, you will still get all of the marks. Okay, times by 100, and that comes out as being 21%. Okay, next one. The student extends the investigation by collecting data on different cars. She records the useful power output, their masses, their maximum speeds. The table shows her data. using information table, discuss the relationships between useful power output, mass, and maximum speed. So what are the things that we can talk about? So if we look at this, what are the relationships we can see? Well, the nice thing is these numbers are increasing. Oh, look, and so are these numbers. So as power increases, speed increases. So because that's power and maximum speed, so greater power is greater. That's the first thing we can say. Second thing that we can say is what it's looking for is using information table. So how do we justify that? We're going to make some kind of correct reference. Okay, so we have to make something. So you can choose from the data. You can, so you can choose from the data. You can choose anything. So you can say, e.g., so 47 kilowatts equals 41 meters per second, whereas 198 kilowatts equals 68 meters per second. So some kind of actual reference to the data. It says that you know what it is you're doing, because otherwise you could just kind of guess at these things. So third mark point. So we've got, so generally it's saying that we've got an increase in mass and we've got an increase in maximum speed. So, it could be this is an anomaly. Okay, so it is what the table suggests. There's not really a reason for that, but a greater mass is approximately equal to greater speed. Okay, so, and again, you can use, so again, you can sort of reference the table. You could reference that there is an anomaly, so that's fine. So then, plus, so some form of data similar to this, so you could say, 721 kilograms, 41, 1, 2, 2, 6, 68, doesn't matter. So that's 3 and 4. 0.5, generally, look, and as power increases, mass increases, similar idea. Larger power, generally, and then again refer to data. Okay, so you're just picking numbers out, picking some things and saying, right, okay, this is what's going on here. Now that's what you can say. Those are kind of the trends, but there is another point which you can say this one is the one that doesn't really work. Okay, so for this set of data and for this conclusion, R does not fit. It's quite bold to make a prediction based on 4 things where one of them doesn't work, but that is something that is helpful to say. Okay, these relationships may be true, but R doesn't seem to work, so maybe not. And there's a final mark, which is anything relevant, which is a lovely. Okay, any kind of further relevant thing that you might do in terms of your calculations. So you might do a power to mass, a power to mass ratio or a power to speed ratio. So you might take this, you might do some form of analysis that's a little bit greater. So you might, if you were very bored, for all of these, go, what is the power to mass ratio? So you could say, I've got 47 over 721, and then 92 over 1143, etc. That's not how you spell etc., but never mind. Just etch. I am not terribly sure I would do that. But again, you're only looking for 4 marks, so any of these. You say this, you get 2 marks. And if you said, greater mass tends to exceed greater speed, if you said that, gets you a 3rd mark. And if you said except for car R, that's actually 4 marks. So you could say that one, do justify that one, and then R does not fit. And that gets you the 4 marks. You do not need to say all of these things. This is just responses that people might give. Right, okay. Last question, getting on there, nearly there. Right, okay, state the formula linking work done, force and distance moved. It's lovely, it's largely just again, work done equals force times distance. We've got a bag of building materials as a weight. Well, the work done lifted the vertical distance to 230 centimeters from the ground. Give the unit. Ooh, 230 centimeters. Well, that is 2.3 meters because I want to go in joules. If I leave it in centimeters, I would actually end up with centijoules. So it's correct, but it's a bit annoying. So I'd have work is equal to 8750 times 2.3, which comes out as being 20,000 approximately to, so it's that 20,000. I think it comes as being 20,125, and this would be joules. You are actually allowed a few other things, like if you do, I mean, it is newtons times meter, so you could say Newton meters, that's fine. You could leave it, if you left it in centimeters, you could leave it as centijoules, that's perfectly fine. A bit weird, but there you go. You do you. The crane takes 7 seconds to lift the bag. What is the mean power output of the crane when it's lifting the bag? So we'd say, again, power is equal to work done over time taken. We are given that's the work done. So whatever number you've used here, remember, you get an error carried forward. If you did the conversion into meters, okay, or you've done it, you can't get penalized twice. So that's 20,000 over 7, which comes out as being 2,900 watts. This is one of the reasons why it's important that you actually do the conversion, because this is finally going to get you to go into watts. We do kind of need that in meters. So if you didn't do the conversion and you left this as centijoules, you'd get marks there, but then you might lose one here because you do at some point need to convert to actually joules. And then finally, we have a stabilizing leg, position on the wooden board. Why the wooden board is used, simple thing, it is going to reduce pressure, or you can say prevent sinking. So it prevents this thing sinking. State the formula linking pressure, force, and area. Pressure is equal to force divided by area. If you were going through and spotting things, I'm just going to multiply these things together. This is where it would go wrong. The wooden board is a square with side length of 0.5. The pressure on the board exerts is 148 kilopascals. Count the force exerted by the board. So again, got another little unit there. So we've got to do, and we need to know length. So essentially, we have to, therefore, first, I've got 4 marks. Lovely. So the first mark is for working out that the area is equal to 0.5 times 0.5. Okay, which is comes out 0.25 meters squared. So that's 1 mark. And then we have to substitute into the equation P equals F over A. So we are going to get 148 kilo. So we're going to have 1,000 is equal to some force divided by 0.25, and then we can rearrange that. So that gives us force is equal to 148,000 times 0.25, and that comes out as being 37,000 newtons. And there you go. That is how to do the test, and that's 28 minutes, so I've got a bit of time, and you have to listen to some of my weird stories. But hopefully that makes sense. If if anything, if you've still got any questions, do feel free to ask. Okay.